The title of this presentation is From Percolation Theory to Operations Research, Competitive Recovery, the Largest Connected Component. To begin with the presentation overview, we'll be introducing percolation and recovery percolation on different types of networks. And we'll first be beginning with an electrical network because this can help describe the distribution of electricity from generators or other centralized electric sources, which can have connections to looking at different components of the large or different structures of the network, from the largest connected component to other types of features that we can look at in recovery percolation, in which we'll be looking to recover different sizes or different clusters which are associated with the largest connected component. And associated with recovery percolation and statistical physics in general, we'll be describing the sharp threshold phenomena, which is related to concepts in statistical physics, which is related to network recovery. And finally, we'll be concluding this short presentation by discussing connections between recovery percolation on electrical networks and applications and prospects for this method to be able to study connectivity in different types of structures arising in other types of networks. So the motivation first that we want to think about come from some images from Wikipedia and other types of books which describe electrical networks which distribute energy. And this is giving one type of example in which there can be different types of electrical networks and power grids which can connect either, New York and Canada, or the West Coast between the US and Canada, and other types of areas in America. And what this is interesting is, as a motivation from another example, which is given in another image in Wikipedia, is that we can see that a lot of the structure of these types of networks have connection with percolation in electrical networks, because it can demonstrate how there can exist different connected components or different edges in the network which are connected to each other, which can be used for distributing some types of fixed amount of voltage or some type of electricity from one area to another. And this is important from a recovery percolation perspective in other structures of the network that we'll also be mentioning in terms of the largest connected component, because it demonstrates that there are some generators or some hubs within these types of electrical networks that are more concentrated and which distribute electricity more from one area of the network to another, in which some degrees or nodes of the graph will have a higher number of connections than other nodes of the graph. And the reference that we'll be looking at and describing how we can make use of this framework, and how it would be of interest for others to continue to formalize these types of ideas within more of the percolation and statistical mechanics literature, is a paper from Smith and others, which is titled Competitive Percolation Strategies for Network Recovery. And a lot of what they're interested in has been related to things that we've been talking about and mentioning, namely, like, if you look for electrical networks and other types of networks, there can be different types of connected components, and there can be the supremum or the largest connected component throughout the whole network. In determining what would be the probability of recovering many connections in the network if we remove the largest connected component and maybe only throw in a couple other more nodes in the connected components that are associated with these nodes in the graph, and what would be the prospect in connections with sharp threshold phenomena from statistical physics. And as we've been mentioning, the recovery percolation model exhibits a sharp threshold. A sharp threshold in statistical physics generally means a very brisk or brief change in behavior, which can be given by, as we vary a certain parameter m, which is included in the recovery percolation model, as we increase the value of this parameter, the value of the sharp threshold increases, namely this value at which t over n, at which the brief change in, or the brisk change in behavior occurs, will be different. And there can be structures and networks with recovery percolation, which is studied also from their paper, in which they give different ways to visualize connected components in network structure synthetic power grids. And the power grid is just like the type of grid that in network that I demonstrated and motivated in earlier slides, in which this can help distribute electricity and other forms of power from a centralized hub, where most of the electricity is generated and then dispersed throughout the remaining parts of the network, or the remaining nodes of the network. And there are many connections between recovery percolation, more standard percolation models. For instance, Keston, he did a lot of seminal work in looking at the incipient infinite cluster or other properties of Bernoulli percolation and making connections between other stochastic processes in a branching random walk. And in this one paper with Keston and Zhang from the 1990s that's published in this open access, which is titled The Probability of a Large Finite Cluster in Supercritical Bernoulli Percolation, they quantify for supercritical parameters in Bernoulli percolation, namely parameters that are strictly greater than a half, because the critical point of Bernoulli percolation is at a half, whether one can quantify the size of the large finite cluster in the supercritical phase. And this is very much relating to the recovery percolation framework, because in recovery percolation, we're trying to see what type of components or degrees or largest connected components of a network that we can recover, which is represented in some graph, in which some nodes can have many more connections than other nodes in the network. And another reference for other classical properties of Bernoulli percolation from many is another one from Dumino-Copan, in which he illustrates introduction to Bernoulli percolation and highlights many types of properties that are enjoyed by Bernoulli percolation, which carry over to some other models of statistical mechanics, namely whether there is an increasing coupling, there's the FKG inequality, which lets one lower bound intersections of increasing events, as well as the Russo formula and ergodicity. And in the paper that we've been describing for the competitive percolation strategy, they demonstrate how the supply and the demand formulation from a European power grid can be formulated as an optimization problem, in which they minimize these two summations subject to some constraints. And I'm not going to exactly go into the constraints, but the structure of the network that they're interested in looking at from the European power grid is given by almost 1,500 nodes, as well as some energy supply demand, which they're able to formulate and study as a minimization problem as a framework for testing their recovery percolation in the largest connected component framework. And there is a potential for being able to apply recovery percolation for other models in statistical mechanics. And by and large, these models are characterized by the fact that they have a different assignment of local rules. Usually in statistical mechanics, we like to look at models which have nearest neighbor interactions. And this is relating a lot to the recovery percolation model, because we can either have connections which are either between nearest neighboring nodes, which are more short range connections, or we can also have longer range connections, which are given by the fact that there can exist a long range percolation model which can exhibit some type of longer range order and longer range connectivity through the largest connected component. And there are different types of models in statistical mechanics which can relate to and can also be studied within this recovery percolation framework, namely to see if we remove some connected components within these percolation models, what would be expected in terms of being able to recover other connected components of the network if we only build in back in some of the structure of the network that we removed from the largest connected component. And some of these models are related, namely the 6-vertex model, which has different types of configurations depending upon if you look at a height function or a line configuration, and it's given by 6 possible configurations in the sample space, which is related to the ICE rule, which is namely a conservation rule in which about every vertex, you have to have the same number of edges pointing inwards as outwards, namely 2 edges pointing in and 2 edges pointing out, as well as a Potts model, which is related to, which can either be cast in terms of a long-range Potts model or a random field Potts model. And the random field Potts model and the long-range Potts model are related to each other just in terms of reflecting upon the definition of the Hamiltonian and introducing different components in the Hamiltonian, either for a random field component or a long-range component through the coupling constants, as well as the random cluster model, which is determined by a probability measure that's supported over the square lattice, in which we can sample a configuration omega, which belongs to the random cluster model, which is related to and can be expressed as in terms of a probability measure normalizing the partition function and multiplying the number of clusters by the number of open edges, p to the number of open edges, and 1 minus p to the number of closed edges. So the conclusions that we provided is that we've introduced percolation and recovery percolation on different networks, and we were interested in looking at a connection between percolation theory and operations research because it demonstrates how different networks can optimize performance and be able to optimize the way in which different types of connections are distributed throughout the network, and how the largest connected component, which is the supremum of all the connected components which in the network, helps us describe the sharp threshold phenomena, because as we had mentioned, as we increase that parameter m, which is associated with a recovery percolation model, the threshold increases, and this brisk or brief change in behavior that's given by a sharp phase transition that's enjoyed by many models in statistical mechanics can occur for later parameters. And in doing this, and in bringing this up in our discussion, we contrasted the probability of recovering the largest connected components within different electrical networks. And finally, we concluded by applying this framework, which can also be studied for other network structures rather than those that are only encapsulated by electrical networks. And thanks for listening.